it starts out with this equation right here. So basically this equation is just saying that at standard conditions, and remember standard conditions are, 25 degrees Celsius and all the right pressures and all of that stuff. But most importantly for this, 1 molar concentration of both reactants and products, 1 molar concentration of all the ions present, basically, right?
Right.
Okay, so this equation is just saying that at the delta G required to get from standard conditions to equilibrium is equal to the natural log of the equilibrium times negative RT.
Right.
So if your equilibrium constant just happens to be perfectly 1, then that delta G required to get from standard conditions to equilibrium is 0 because standard conditions are equilibrium. If all concentrations are 1, then your Q is 1, therefore you're at KEQ, therefore it'd be 0.
Right.
Q equals 1 at standard conditions, right? So if your KEQ is less than 1, then the delta G to get there would be positive.
Right.
Because if KEQ is less than 1, the natural log of that KEQ is going to be negative, meaning the delta G would be positive here.
Right.
Or if your KEQ is greater than 1, meaning favoring products, then it would be energetically favorable to get to equilibrium from standard conditions.
Yes. Okay.
Okay. So then the more important equation that we need to think about, and this is like the main thing, is this equation, where we've got the delta G of the reaction not at standard conditions, set equal to the delta G of the reaction at standard conditions plus RT ln of Q rather than ln of KEQ.
Okay.
And so basically what that's saying is that the energy necessary to get to equilibrium from any Q, not just from standard conditions, right? Because this is any value of Q. And so that's represented by this in that equation, is equal to the delta G required to get to equilibrium from standard conditions plus RT times ln of that specific Q. Okay, so we haven't invoked the standard potential just yet. Does that all make sense to this point?
Yes.
Okay. So then the last equation that we need, and I hadn't written this down in the notes yet, but the last equation that we need is the one that we started with the other day, which is that delta G of the reaction at standard conditions is equal to the negative NFE of the cell. Okay.
Yes.
So
right.
once we have that equation, we can just sub this bit in for the delta G of standard conditions. See what I'm saying?
Yes.
Okay. At that point, what we end up with is the overall delta G of the reaction is equal to negative NF E of the cell plus RT ln of Q.
Right.
Okay. And so then the very, very last thing that we need to do in order to get the Nernst equation is calculating the E of the cell needed to establish that overall equilibrium between the electric equilibrium and the concentration gradient.
Right.
Okay. So then very last thing that we need here is to take this negative NF, divide basically the whole equation by negative NF. So if we just divide the whole equation by this.
Right.
Okay. So if we divide the whole equation by that, delta G divided by NF is identical to the E of the cell. Yeah, exactly.
Yeah.
So you end up with E cell, but notice that's not at standard conditions because we divide the delta G that's not at standard conditions by it. So that's our EMF, or like E cell not at standard conditions is equivalent to EMF or is equivalent to membrane potential. Basically. So that's the membrane potential needed to balance these two gradients, the electric gradient plus the concentration gradient, because we end up with E of the cell is equal to E of the cell at standard conditions minus, because we divide by negative NF, minus RT ln of Q, RT divided by NF ln of Q.
Yep.
And that's the Nernst
equation.